So Unit 5 in this class is, excuse me, about gases. There is no Unit 5 exam, but you will see just a sprinkling of questions over gases on your comprehensive final. A lot of things about gases are pretty intuitive. You're like, oh, I've seen that before, or that makes sense. And these are, this first part, I just want to kind of talk about some non-quantitative things about gases. So gases are generally compressible. So that means that, for instance, over here, you can, this is a plunger, and you can see these particles. These are gas particles, and as the plunger moves down, the gas particles get closer and closer. If we compare that to liquids, we push the plunger down, and liquids are generally not compressible. So gases are compressible. I'm going to go back and forth to that slide. Another thing about gases is they will always take all the space you'll give them. So gases take on the volume and the shape of their container. I think we covered this clear back in the first unit of material. I just love gases. You can kind of see they're all moving around. Another thing about gases is that related to their compressibility, gases have, if you want to go get the density of a gas, density is a ratio of mass to volume. And if you can keep changing the volume, then you have changing density. Now, I'm not saying that it has no density. I'm just saying it will vary for gases. Another thing about gases is that their densities are relatively low compared to those of liquids. So this kind of boggles my brain, but because I feel like somehow it's missing some information. If we were to take this can of 12 ounces of fluid, 355 milliliters, and if we were to convert it all to vapor, it would then be equal to a volume in 1,700 cans. Now, to me, we've got a temperature issue somewhere in there, but anyway, the gases are a lot less dense than liquids. This is a good one. Gases will always want to mix with their buddies. So kind of from left to right, here's a blank cylinder. Here's a cylinder with just carbon dioxide in it. And here is a cylinder that actually, from the carbon dioxide, we added argon. And notice that given time, the argon and the carbon dioxide are going to form a homogeneous mixture. They just do, and it makes sense, right? One last one is that we're going to talk more about pressure, but gases will exert a pressure on the walls of the container that's holding them. So it kind of looks like this. This is our walls of our container. Okay. Can you see the gas particles banging against the bottom of the container in this case? So we'll talk more about pressure coming up. When I work problems, gas law problems or gas problems, a lot of times I will draw my little box and I'll draw my little gas particles, and sometimes I'll kind of show them banging around inside my box. And in order to characterize basically a fair number of information about that gas, what I need to know is the pressure that the particles are banging up against the container walls. I need to know the temperature at which the gas particles are moving around. I need to know the volume of the container, and I need to know the cute number of moles of gas particles that are in there. Notice that in those four things, I didn't say I needed to know what sort of gas it was. Is it carbon dioxide or argon? I just think that is so cool. So both argon and carbon dioxide will, we say, behave the same with regard to these four variables. I just think that is so cool. So we need to talk about pressure a little bit. Pressure is a ratio of force divided by area. So it's force divided by the area over which that force is applied. Well, force is equal to mass times acceleration. I'm not going to focus on that as much as the units of force are newtons, which can be broken down to kilogram meters per second squared. Then if we go back to pressure, pressure is force, which are units of newtons, divided by area over which the force is applied. And a good, strong unit of area would be meters squared. Now, so Pascal, PA, actually is a unit of force, a unit of pressure. Pascal is a unit of pressure, and we're going to see that that's not the one that we're going to kind of run with. But it's a good one. So units of pressure, units of gas pressure. We do a lot with atmospheres. Actually, 1 atmosphere is about, as we're walking around in general, what the pressure of the gases in the room are at sea level. Not to say pressure doesn't rise and pressure doesn't fall, because it does. If you're a weather bug, you know that. 1 atmosphere, another unit of measure we deal a lot with is millimeters of mercury. MM means millimeters. Hg, of course, is the element mercury. We've been talking about conversion factors in this class, and one that you might want to commit to memory or jot down on your card or just have a sense of is, with regard to pressure, 1 atmosphere is exactly equal to 760 millimeters of mercury. That would be, I guess, by definition. We have kilopascals. By the way, 1 atmosphere is equal to 101.325 kilopascals. 1 atmosphere is also equal to about 1 bar. This one, if you've ever heard, looked at your tire, PSI, pounds per square inch. Tires are what, 35? It depends on what kind of vehicle the tires are holding up. But this is pounds per square inch, lb per in squared. As we're walking around on Earth, about sea level, you're looking at 14.7 psi is the pressure that the nitrogen and oxygen gas particles, mostly all the gas particles in the atmosphere, are exerting with that pressure. So, a few more things. Millimeters of mercury, of course, 760 millimeters of mercury is exactly equal to 1 atmosphere. A unit of torr comes in handy sometimes, the pressure unit torr. And as it turns out, the millimeter of mercury and torr are exactly equal. Bar, we do a lot of using the pressure of bars in meteorology. An isobaric map would be one that actually connects locations with the same pressure, and those would usually be in bars. All right, so this is actually a table from your textbook that that you might want to refer to here and there. Again, the ones that these two right here are kind of, as I've worked gas problems for this class, that's probably what I'm looking at. Okay, what else do we need to know? So here's a mason jar with those cute little gas particles in it. One of the things we're going to look at is what happens to the pressure of the particles if you increase them. And you probably say, well, the pressure increases. And you're right. So the difference between this jar and this jar is we have added more particles. This is actually what I would say. You increase INC for increase N, which is number of moles. Okay, and what happens? You increase INC P, pressure. So this slide actually is talking a little bit about the millimeters of mercury. Remember we said that 1 atmosphere is exactly equal to 760 millimeters of mercury. Well, how can you get like a length or a distance an element and relate it to pressure? Well, this is actually a mercury barometer. And the way this works is this is liquid mercury down here. It looks kind of dangerous, doesn't it? And what's happened is there's a glass tube that is open at one end. So the glass tube is open down here and it's closed up here. And so what they did, or in order for a mercury barometer to work, you have to fill the tube with mercury and then invert it here. Now what's going to happen then is this distance right here, the column of mercury that rises up the tube or falls down the tube, that length actually is an indication of the pressure of the gas particles in the atmosphere. And this is how this works. Can you kind of see this blue arrow? It's showing you that actually there will be pressure exerted on the liquid mercury here, and the more this pressure, if this pressure increases, the mercury that goes up the column increases. So, millimeters of mercury. Okay. So what I'm gonna do is take those 4 variables, P, V, N, T. These are the 4 variables that fully describe gas particles. Okay, and I'm going to take them in pairs. So first I want to focus on pressure and temperature. Now we're going to assume that actually in this case that volume and number of moles are going to hold constant. And this is a very common thing. How do I say this? If you have a balloon or, I don't know, a water bottle, and it has a little bit of headspace at the top with a gas in it, if you cool down that water bottle, we're going to cool down the water bottle, it's actually going to cool down, or the pressure, it's going to cool down your gas particles, and as they cool down, they'll go slower, and so the pressure will cool down. So in other words, if you lower the temperature, what's going to happen is you're going to end up lowering the pressure. If you raise the temperature, you're going to end up raising the pressure. And to me, that makes sense. What pressure those gas particles exert are a function of how much kinetic energy they have. And as you monkey with the temperature, you're monkeying with their kinetic energy. So we could actually write a mathematical statement that links pressure and temperature this way, where this thing is called a proportionality symbol. Kind of looks like an infinity symbol with a byte taken out. We would say that the pressure is directly proportional to the temperature. And that means as one goes down, the other goes down. As one goes up, the other goes up. Okay, so they're proportional to each other. All right, so you get the idea? So P, V, and T. So now I want to focus on pressure and number of moles, and I'm going to hold temperature and volume constant. Okay, so that's assuming that they're constant. So in this case, we actually looked at this a minute ago, where we had the two mason jars and we kind of doubled the gas particles. So in that case, as we increased the number of moles, what happened was it increased the pressure. And by golly, if you were to take some moles of gas out, guess what? It would decrease the pressure. So again, we have what's called a direct proportionality between these two variables. And so we can write that mathematically by saying pressure is directly proportional to number of moles. Well, you know what? Something's got to be not directly proportional. So I'll take P, V, and T. So now I want to look at pressure and volume. And to me, and we're going to hold these constant, and we're going to vary these. Okay. So to me, if I take a balloon and I squeeze my balloon, so if I squeeze my balloon, I'm actually going to decrease the volume. What would happen to the pressure? Well, if I decrease the volume, squeeze my balloon, actually I could make it pop. And the reason is I'm applying more and more pressure to that smaller volume. So here we have something that as one goes down, volume goes down, pressure goes up. And I could convince you that if volume goes up, those little gas particles have more room to run around in, and we're going to see that actually the pressure is going to go down. So these are what we call inversely related. They're inversely proportional to one another. So the way we show that mathematically is this. Again, this means proportional. We can say that the volume is proportional to the inverse of pressure. And that's the same thing as saying that as one goes up, the other goes down, one goes down, the other goes up. Okay. So this is a look at pressure and volume. Notice that as I decrease the pressure, decrease the volume. As I decrease the volume, I'm going to increase the pressure. All right. I know we talked about temperature, clear early on in this course, I think, but just to kind of remind you, because I want to link temperature now, because check this out, P, V, N, and T. Oh, I need temperature, right? Temperature, remember, is not the same thing as heat, thermal energy, but what temperature will do is tell you the direction that thermal energy will move. And that just means like if you have, if I have A and B, and A and B, and A is hot and B is cool. If we go ahead and open a conduit between the two, allow them to share material or share thermal energy, we're going to see that actually thermal energy or heat is going to go that way. So I need to talk about temperature scales just to remind you that the most sophisticated temperature scale is the Kelvin temperature scale. In that it actually has, it's what we call the ratio level, and it's 0 means the absence of something. It means the absence of thermal energy. So 0 Kelvin is what we call absolute 0, and you can't get any colder than that, because at 0 Kelvin, all molecular motion stops. Pretty cool deal. And I want to mention this quick conversion factor. Now, the Kelvin scale is the most sophisticated, but the Celsius scale is also metric. These are both metric. So oftentimes it's possible that you are given Celsius temperature and you need Kelvin. So what you're going to do is add 273.15. If you need to go the other way around and you're given the Kelvin temperature and you need Celsius, you're going to take Kelvin temperature and subtract 273.15 units. So that's one that you might want to put on your final exam card. I don't know. It's a thought. So I'm building up to something that's called the ideal gas law. The ideal gas law. Well, in order for the ideal gas law to work, we need to talk about when a gas is behaving ideally, what does that mean? Well, there are two assumptions, and what they say about assumptions, you shouldn't make them if you're not sure. But the two assumptions that are made that if a gas is behaving ideally are this. One is that there are no connections, no forces that connect the gas particles together. And two is that basically the gas size is negligible. Like 0 size, you're like, really? Well, the gas size is negligible, or the gas particle volume, it does not count. It's insignificant compared to the volume of the container it's banging around in. As small as molecules and atoms are, I can about buy that. So here's the deal then. This bit about no connections, no forces between the gas particles, that's really pretty good at high temperatures. You figure at high temperatures, they don't have enough, they have so much kinetic energy, they're not going to be stuck together. That's the way I think of it. The other thing about the gas particle having basically negligible volume compared to the volume of the container it's banging around in, this works if you have if your container is relatively sparsely populated with gas particles. In other words, if you're at relatively low pressures. So just to kind of summarize then, if our gases behave most ideally at high temperatures and low pressures. If you stay in chemistry, we'll kind of talk about how to kind of correct for low temperatures and high pressures. But so I've kind of built up to what's called the ideal gas law equation. And here you go. Ideal gas law equation. Okay. So here we go. It just simply says that, I'll go ahead and draw my little box here. Here's my particles. I'll give one a little bit of, show a little bit of motion there. P, V, N, T. So these variables that we've already talked about, of course, P is pressure, V is volume, N is number of moles, and T is temperature. Those four variables are related to each other this way. And the one thing I didn't introduce, or I'll introduce in the next part of the lecture slides, is that R is the ideal gas law constant. Ideal gas law constant. And I'll kind of tell on myself, I usually have to look it up, but you might want to put it on your card. But it is the constant that links these four variables. It is so cool.